So let's continue with our discussion and explain the Maxwell equations. We are going to explain the second law of Maxwell's, that is the Gauss's law for magnetic field. Remember earlier we explained Gauss's law for an electric field. That was the first law. Second law is Gauss's law for magnetic field. So what this law states, there are two forms like differential form and the integral form. So the first form, which is differential form, says that divergence of the magnetic field through the closed surface of a volume is equal to zero, is always zero. So for example, let's say I have a volume and there is a charge. In earlier case, for the first law, we saw there was a charge, positive or negative, and there were like field lines emanating from this charge. So we took a very small portion of this volume, which is a surface area, and we calculated the electric lines, which we determined, which we called it as a net flux coming out of this surface. So that flux was proportional to Q over epsilon naught. And we said that del dot E was equal to Q dot epsilon naught. So divergence of electric field was proportional to the charge enclosed by that surface in that volume multiplied by this reciprocal of this constant 1 upon epsilon 0. But in the case of magnetic field, the divergence of the magnetic field through any closed surface, let's say you have a closed surface and the divergence of the magnetic field is equal to 0. It means there are no magnetic field lines coming out of this surface enclosed by the surface. So the net flux for the net flux, or we call a net magnetic flux is equal to 0, and that is what this equation is. Okay, so this law states the divergence of the magnetic field is always 0. So in other words, it indicates that there are no magnetic monopoles, isolated magnetic charges. So it means there are no magnetic charges enclosed by the surface within that volume, unlike the electric field case. Okay, so let's say you have a magnet, a bar magnet, where you have a north pole, you have a south pole. So there'll be always two poles for a magnet. There'll be a no such case that you have a magnet with only single pole, right? And that will give the magnetic charges. No isolated magnetic charge will be there. So for example, if you break this magnet, so it's not the case that this particular magnet will be called as N North Pole and this particular piece of a magnet will be termed as South Pole. No, this won't be the case. So what would be the case? Each piece will have its North Pole and South Pole, North Pole and South Pole. So that's the first form. Second way to understand the Gauss's law for magnetic field is again to understand its integral form. So integral form is that this equation is explaining this equation. So we'll see what this equation means. It says the double surface integral of the magnetic field over the surface area within that volume is equal to 0. So this equation and the previous equation is essentially saying the same thing. Okay. So you see now, for example, you have, let's say, a sphere, or let's say a cube, or any other shape which is enclosed, completely enclosed, and it has small surface. So the magnetic field lines coming out of this surface is always equal to 0. There is no diversion of the magnetic fields because there are no magnetic monopoles. So the magnetic field lines, or in other words, the magnetic flux through any of these surfaces is going to be 0. Okay, for this case. So this equation says that S is the any closed surface, ds is a vector whose magnitude is a small area that we consider in any of this shape, the small area, in infinitesimal piece of the surface area, and whose direction is outward. So it's out of plane. This PowerPoint I am presenting you, it's out of plane. And his direction is outward pointing to this surface normal. So it's out of plane of this PowerPoint. So the left side of this equation, which is the double integral and the divergence of B dot ds, this is left side, is nothing but the net flux. Net magnetic flux. And we say that this magnetic net magnetic flux or magnetic field lines out of the closed surface, any small piece of surface area, is saying that it is going to be 0, which is equal to the right side. Okay. On the other hand, let's say we have such kind of shapes. So we have surface like this, or surface like this, or surface like this. So these are not the closed volumes. Okay, these are not the volumes. So basically we have these surfaces. So the magnetic flux through any of these surfaces is not necessarily 0. So there may be such cases where you have such surfaces. So we'll not say that the divergence of the magnetic field lines out of these surfaces is 0. Okay. In another representation, to understand the Gauss's law for magnetic field, which is our second law. Okay, remember the first law was Gauss law for electric field. Second law is the magnetic field. So in integral form, it says that the divergence of the magnetic field lines is equal to 0. And in other words, we understand that, let's say we have a bar magnet. It has a south pole and the north pole. It has another case, south pole and north pole. So it says that this equation states that for each volume element in the space. So you have some small volume, and for each volume element in the space, there are exactly the same number of magnetic field lines entering and exiting the volume. So you have that volume, and within that volume, you have this magnetic field lines creation. So the number of lines entering uh, entering and exiting that volume are going to be the same. So the net magnetic lines would be, net magnetic field would be 0. So that is what this equation says. That same is the case here. You see the number of lines entering are going to be equal to the number of line exiting with this volume. So that was the end of second law.